Alright, here we're looking at solving polynomial equations. And in order to do this, we're going to solve essentially by factoring. So what we need to do is we need to learn a little bit more about factoring before we can proceed. And the one special case that we're going to look at here is a sum or difference of cubes. When we're doing this, just like a difference of squares, we're looking for two perfect squares that are being subtracted. Well, now for a sum or difference of cubes, we're looking for two perfect cubes that are being subtracted or two perfect cubes that are being added together. All right, and when we do this, really this is just essentially memorization of a pattern. The only real way to do this is just going to be using this shortcut, okay? So just remember, when you see a sum or difference of cubes, two perfect cubes that are either being added or subtracted, we're going to break this down into a binomial and a trinomial, okay? So a little piece and a big piece. And I always start by filling in the signs, and I remember that by using SOAP. Same opposite, always a plus. So SOAP, if you can remember SOAP, you should be able to come up with these signs. So right here I had a plus sign, so this sign is the same, this one's the opposite, this one's always a plus. Here I have a minus sign, this sign is the same, this one's the opposite, this one's always a plus. Okay? So we use SOAP to remind us how to set up these signs, and then from here we just have to memorize this pattern. And the pattern is, well, we start with this binomial. I essentially take the cube root of this guy and put it here, that's how I get the a value. I take the cube root of this guy and I put it here, that's how I get the b value. Alright? And now I take this a value and I square it and it goes here. I take the b value and square it and it goes here. And then I multiply the a value and the b value and it goes in the middle. Okay? And so really it's just memorization of how this pattern works. So again, I set up the binomial and the trinomial. I fill in the signs, same opposite, always a plus. I take the cube root of each piece to get the binomial. And then I square the first piece to get the first term of the trinomial. I square the last piece to get the last piece of the trinomial. And then I multiply the two pieces to get the middle piece of the trinomial. All right? And here's what this looks like when we kind of put it into practice. If I look at this guy, x cubed is a perfect cube, 8 is a perfect cube, so this is a sum of cubes. So it's going to factor into a binomial and a trinomial. So I always set up the binomial and the trinomial first. So a little set of parentheses and a big set of parentheses. And now I fill in the signs. Since this is a plus sign here, my first sign is going to be the same, which is a plus sign, then the opposite, which is a minus sign, and then always a plus. SOAP, same opposite, always a plus. And now I take the cube root to get the binomial, so the cube root of x to the third is x. The cube root of 8 is a 2. And now that I have the binomial, I basically take this first piece and I square it, and I put it here. So that's x squared. I square the second piece, and I put it back here. That's a 4. And then I multiply the two pieces. X times 2 gives me a 2x, and I put it in the middle. And that's it. Now this thing is factored, and really it's just a matter of committing that pattern to memory. Okay? If I do the same thing with the next guy, again, it's a difference of cubes this time. I've got two perfect cubes being subtracted. So I set up a binomial and a trinomial. Same opposite, always a plus, SOAP. So this sign is the same, this one's the opposite, this one's always a plus. Now I take the cube root of each piece. The cube root of x to the third is x. The cube root of 8 is a 2. And now I take that first piece and square it. That's x squared. I take the second piece and I square it. That's a 4. And now I multiply the two pieces, and that's a 2x. And notice when I multiply, I ignore the signs. I just do the x times the 2, not an x times a negative 2. Keep in mind that once I plug in those signs, once I use SOAP, I don't want to change those signs for any reason. Okay, so I ignore the signs after that. All right? And when you look at these two examples, obviously the answers are almost identical. The only difference between a sum or difference of cubes is the pattern of the signs. Okay? Everything else, the setup is exactly the same. Okay? If I look at this one, again, this is a sum of cubes. I've got all perfect cubes and they're being added. So I'm going to split this into a binomial and a trinomial. I use SOAP, so same opposite, always a plus. And now I fill these in. The cube root of 27x to the third is a 3x. The cube root of 1 is a 1. And now when I square that first piece, 3x times itself, that's a 9x squared. I've got to square each piece. The 1 squared is a 1. And now when I multiply the two pieces, that's a 3x. That goes in the middle. All right? So again, it's just a matter of memorizing this pattern. The next one, this is not a sum or difference of cubes. 4 is not a perfect cube. Neither is 32. But what I do notice here is this has a greatest common factor of 4, so I can factor the 4 out. That's an x cubed minus 8. And now x cubed minus 8, that is a difference of squares. I can factor it into a binomial and a trinomial. This sign is the same. This one's the opposite. This one's always a plus. The cube root of x to the third is x. The cube root of 8 is 2. When I take that first piece and square it, it's an x squared. When I take the second piece and square it, it's a 4. And then when I multiply the two pieces, it's a 2x. Okay? So again, we're memorizing that pattern. And the thing about shortcuts like this is, again, they only work when I factor out the greatest common factor first. So make sure you factor out that 4 first. Okay? So when I look at these things, it says to factor completely using a combination of previous methods. When you think about all the methods that we know for factoring, the first thing we always look at is factoring out the greatest common factor. The second thing we learned was factoring by grouping, where we put them in groups of 2 and then factor out the greatest common factor from each and then look for common polynomials. The next thing we learned was factoring trinomials, where we build a bridge and split up the middle term, all that. The next thing we learned was some of our special cases, like difference of squares. Remember, difference of squares factors into conjugates. One's a plus, one's a minus. And then the fifth thing we just learned a moment ago is a sum or difference of cubes, okay? And so when we look for these things, we're kind of going to look for them in that order, all right? Because those are the methods we learned, and we learned them in that order. We're going to look for them in that order. So for this one, I look for greatest common factors. There is no greatest common factor here. There's nothing that all 4 terms have in common. So I move on to something like factoring by grouping. And factoring by grouping is great to use here because I have 4 terms, so I can easily put them in groups of 2. And that's one of the giveaways for factoring by grouping. If I have 4 terms, typically factoring by grouping is something that I at least want to try. All right. Out of this first group, I can factor out an x squared. That leaves me with an x minus 1. Out of the second group, I can factor out a negative 9. That leaves me with an x minus 1. And now, because I have a common polynomial here, this x minus 1, I can factor that out. So if I take out the x minus 1, it leaves me with an x squared minus 9. And now an x squared minus 9, that is a difference of squares. So I can factor that into an x plus 3 and an x minus 3. And again, I have to make sure this thing is factored completely. So I have to keep going until all of it is factored as far as it can be factored. Okay? For the next one, the first thing I look for is greatest common factor, which this has a greatest common factor of 5x. So I factor that out. That leaves me with an x cubed plus 27. Now x cubed plus 27 is one of the cases we just learned. That is a sum of cubes. So I'm going to factor that into a binomial and a trinomial. I use SOAP, same opposite always a plus, to fill in my signs. The cube root of each of those is an x and a 3. And now when I square the x, it gives me x squared. When I square the 3, it gives me a 9. When I multiply the 2, it gives me a 3x. So these are my factors. And you can try factoring that trinomial by building a bridge, 2 numbers that multiply to a 9 but add to a negative 3, but it's not going to work. Okay? So this is factored as far as it can be factored. And that's it. If I look at this one, x to the 6 minus 64, this is actually 2 different things. I mean, greatest common factor doesn't work. Factoring by grouping doesn't work because I only have 2 terms. This is actually, it's not a trinomial, so I'm not going to build a bridge, but it's actually a difference of squares. It's also a difference of cubes, all right? But what we want to do here is always factor it in the order we learned it. Always do difference of squares first. It just works out better. So I'm going to factor this as a difference of squares. So these are going to factor into conjugates. So it's going to be an x cubed plus 8 and an x cubed minus 8, all right? And now when I look at each of these, x cubed plus 8, that's a different sum of cubes. That's going to factor into a binomial and a trinomial. X cubed minus 8 is also a difference of cubes. That's going to factor into a binomial and trinomial. So I'll factor this first one. Same opposite, always a plus. I take the cube root to get an x and a 2. When I square that x, it gives me an x squared. When I square the 2, it gives me a 4. When I multiply the 2, it gives me a 2x. Okay, that's the pattern that we're going with. For this one, same opposite, always a plus. When I take the cube root, it gives me an x and a 2. When I square that x, it gives me an x squared. When I square the 2, it gives me a 4. When I multiply the 2, it gives me a 2x. And so now this thing is factored completely. I can't factor those trinomials any further. So that's it for this one. Okay, so we've got to keep looking for things that we can factor until it's factored completely. All right. If I look at the next one, again, I start off the same way. I always look for greatest common factor. This has a greatest common factor of x, which factors into an x to the 4th minus 13x squared plus 36. And now from here, factoring by grouping is not going to work. Factoring trinomials, well, this is a trinomial, so maybe I would look at this and maybe try building a bridge and coming up with a 36, and the 2 numbers are a negative 9 and a negative 4. But the question is, what do we do with that negative 9 and negative 4? We know what to do when we're dealing with an x squared minus 13x plus 36. What would we do with it when it's an x to the 4th and an x squared? Okay? And this one is actually going to factor this way, and this is the next thing we're going to look at. This is going to factor into an x squared minus 9 and an x squared minus 4. So I factor it like a trinomial, but instead of an x, it's going to be an x squared for each. And now each of these is a difference of squares. And what we call this thing, we say that this thing is quadratic in form when we look at this. Quadratic in form means it looks like a quadratic. It looks like ax squared plus bx plus c, but maybe I have some higher exponents. All right? And so when we look at something like this guy, quadratic in form means it kind of looks like this. It kind of looks like I have something squared and then something to the first and then a constant term. Okay? And so when I look at this first example, I've got x to the 6th minus 10x to the 3rd plus 21. This is quadratic in form because when you think about it, this is like x to the 3rd squared. That's what x to the 6th is. I multiply the exponents. This would be like a minus 10. That would be x to the 3rd raised to the 1st power plus 21. So we can see something squared, something to the 1st, constant term. And so like if I replace that x to the 3rd, let's call it u. I'll say u equals x to the 3rd. Then I would have u squared minus 10u plus 21. And if you factor it that way, you build a bridge, you come up with a u minus 7 and a u minus 3. Tried to write an x like a crazy person. Now when you think about it, u was actually an x to the 3rd, so what I have here is x to the 3rd minus 7 and an x to the 3rd minus 3. Okay? And we wouldn't actually do substitution. Just recognizing that it's quadratic in form, I can go right to this answer. Okay, I still build a bridge, I still come up with the two pieces of the binomial, but instead of an x minus 7 and x minus 3, it's an x cubed minus 7 and x cubed minus 3. Okay? And the reason for that is because they have to multiply to an x to the 6th. And when I combine those like terms, it's got to be an x to the 3rd in the middle here. Okay? So when it's quadratic in form, and we should start to recognize this pattern. When you saw the last one was an x to the 4th and x to the 2nd. This is an x to the 6th and an x to the 3rd. Here's an x to the 4th and an x to the 2nd. The next one you can see is an x to the 8th and x to the 4th. See, the pattern here is that this middle term, the middle exponent, right here has to be half of this guy, okay? Because that means that it's that thing squared because of our rules of exponents. So this one's quadratic in form. I build a bridge, two numbers that multiply to a negative 12 but add to a negative 1 or a negative 4 and a positive 3. So this is going to factor, instead of an x minus 4, it's going to be an x squared minus 4. Instead of an x plus 3, it's an x squared plus 3. And then from here I do as much factoring as I can. X squared minus 4 is a difference of squares. That's an x plus 2 and an x minus 2. This guy I can't really do anything with, so it's going to stay the way it is. Okay? Now it's factored completely. For this one, it's quadratic in form. X to the 8th, x to the 4th. I build a bridge. Two numbers that multiply to a negative 8 but add to a positive 2 are going to be a positive 4 and a negative 2. So it's going to be, instead of x plus 4, it's going to be x to the 4th plus 4. Instead of x minus 2, it's going to be an x to the 4th minus 2. And there's nothing else we can do here. That x to the 4th plus 4 is a sum of squares which doesn't factor. Okay? And then when we look at this last one, this is not quadratic in form because it's an x to the 5th and an x to the 3rd. Really, if we wanted this to be quadratic in form, this would have to be an x to the 6th. So because it's not quadratic in form, because it doesn't fall into that category, that pattern, I can't build a bridge. I can't do anything with this one. So I'm just going to say it's prime. Okay?